the methods and application. Thank you, Juncheng, please.
Okay, thank you, Talk, and okay, and welcome everyone. And this is my second lecture, talk in this lecture series. So let's go ahead and repeat what I did last time. So in the last time, I talked about the finite dimensional reduction method, and the model problem I took is this nonlinear Schrodinger equation. So we have Epsilon square Laplace u minus v of xu plus u to the power p. And so we solved the problem in two steps. First, we solved the problem up to some Lagrange multiply. So with some orthogonality condition. So, and we solved this by using the fact that our building block is non-degenerate. This is very important. And then we derive some upper estimates. And so we have the both inner and the outer estimates for the problem. Okay. And then the existence will follow from the upper estimate. And the second step, we adjust the parameter lambda. Okay, we have a parameter lambda here in this configuration space, so that all the Lagrange multiply equals 0. Right? So there are two methods I introduced last time. One is the direct method, just directly compute what is C lambda, and show that you have a stable critical point or something, or use a five-variational reduction. So if your problem has a five-variational structure, okay. So, before I take on this infinite time dimensional reduction, which I'm going to talk about today, let me talk about some recent application of finite dimensional reduction method. I think these applications show the broad how you apply this method, even in the situations in which you think you cannot apply. Okay? So the first application I'm going to talk about is the Clang-Gordon equation. So let's think. So in the model problem I discussed last week, we have a small parameter and we have a potential, right? So so we need both small parameter with those singular perturbation, and we need the potential to do the second step, okay, to construct to do the reducer problem. So both problems both factors are important, okay. So okay, so in the first application, I will describe another model problem in which neither factors are present. Okay, so there's no small parameter, there's no potential. Okay, and so for this problem, how do we apply the finite dimensional reduction? We have no no perturbation. Everything is fixed. Okay, so this is called a Clang-Gordon equation, right? Let's think, and we want a finite energy solution. So the question we want to answer is the following: does the finite energy solution assumption or the decay condition, so assume U decays at infinity, impose some kind of symmetry on the solution? Right? So we know the answer is yes, right? If U is positive, and this is the classical result of the Gadas-Limberg, and says if you have a positive solution which decay to 0 or finite energy solution, then U must be necessarily reduced symmetric. So you have some symmetry. You have the reduced symmetry, right? Reduced symmetry. Okay, so what about sign-changing solution? Sign-changing finite energy solutions. So surprisingly, the answer to this question is negative for sign-changing solutions. Right? And in fact, we prove with Weber Au, my former student, and Monica Musso and Frank Parker in 2012, we prove that there are infinitely many finite energy solutions to the Clang-Gordon equation, which has but has no symmetry at all. Okay, it's a complete chaos. The solution is completely, there's no symmetry, okay? There's no symmetry. And of course, all this solution will be non-radially symmetric. So this, okay, so how do we use the finite dimension reduction to construct sign changing solutions? Okay, so the construction of a non-radial finite energy solution is by reduction method, right? So what is the perturbation parameter in this problem? So now we don't see any parameter here, right? You know, if you look at this problem, right, this is a Clang Gordon. There's no parameter here, right? There's no small parameter here, okay? So what is the perturbation parameter? So, and we use the number of spikes, the number of bumps as a perturbation parameter. So somehow we artificially create a parameter, which is the number of spikes. And this is ideal due to we use this idea for other problems, right? With Shushen Yan in 2010. So we use the number of spikes as a perturbation parameter. So let us set this problem as a finite dimension reduction and to see how we solve the problem. Right? Now let me just emphasize that in this problem, there's no small parameter. There's nothing. The problem is fixed. Okay. So the construction, we want to use a finite dimension reduction. So we take two finite points in the compass plane, right? Positive spikes and the negative spikes, and so we take the W as the positive, the ground state, and we'll put the W in the positive points and the negative W in the negative points. So, and we want to look for solutions like this type. Okay, so positive and the negative, positive and the negative. Okay, and these are two sets. Right now, to make sure this is a good approximate solution, we need to assume that the distance between the spikes must be large. Because if the distance between the spikes is small, then you don't see separation, right? You don't see the separation. So if we assume the distance is small, is large, then you can compute easily that, you know, the area is exponentially small, right? This is very easy to see. The area is exponentially small. Okay, so this is the basic fact. So if I assume you have put the spikes positive and the negative, and if the distance between the spikes is large enough, this is a good approximate solution. This is our first step. Right? Okay, so how do we do the reduction? Okay, so we do the usual reduction. And just like before, in the first step, we solve the problem up to some Lagrange multiplier. Okay, so the Lagrange multiplier I write in this form, which is Fz. So think about Fz is like a force at each point. Okay, so this is the Lagrange multiplier. We can solve this, right? We can use the finite dimensional reduction method to solve this. Now, the only thing we need to take care is that the RP estimate should be independent the number, right? You don't, okay. We want all the estimates should be independent of the large number because we're going to use this large number, this K, as our perturbation parameter, okay? And in the second step, we found the set of points for which, so that the Lagrange multiplier equals it, right? So this is the reduction method. This is what we're going to do. So, and the first step is very trivial, is as before, so I will not talk about this. As I said, all we need to take care is all the estimates should be independent, the large number, okay? Independent the number of spikes. The problem is the second step, okay? How to find the set of points for which this is zero, okay? How do we use the small prime, the number K as the parameter? Okay. So let's first compute the Lagrange multiplier. So the Lagrange multiplier is you compute is formula is the interaction between bubbles, between the spikes, right? The interaction between the spikes. And the interactions are exponentially small. And there's a sign, there's either plus or minus. If it's a positive bubble, it's a plus. If it's a negative bubble, it's minus. So you can compute the interaction, okay, explicitly, right? Interaction explicitly. Now, but what we notice that because the interaction is exponentially small, what we need to compute, we just need to compute the neighborhood, the neighboring, okay? The closest neighbor, okay? And away from this, we just need to compute how all the neighbors of in the big set, because far away, this will be too small, okay? So let's assume all the points, you know, the distance is like L order, okay? Right? They're the same order. The distance is the neighborhood, you know, is like L order. And then you do, okay, some small computation, okay? And you look at all the neighborhood and you do a computation of the force. And this is the condition you're gonna get. So at each place, and you look at the neighborhood, all the neighborhood, and then each point will give you a force, they call it eta, okay, A. And what you need is that all the force should be balanced, okay? And all this force will be balanced, should be balanced. So this becomes a network. Think about this is a network, right? At each place, at each of the edge, you assign some force, and the positive or negative force. And then you want all this at each point, all the forces balance each other. So this becomes a graph theory, right? A network problem is to find out the points, some forces, so that, okay, so that this is a balance. So this is a necessary condition, right? And so we need these two conditions to satisfy. But then this is not enough because we need to perturb this, right? We need to perturb these conditions, right? And so we need this network we call it flexible. So the network should be flexible, closable, and balanced. So the network should be balanced, and this is means it's closable and flexible. So, and for the definition of this, you know, this concepts, you can look at the paper and to see what the definition. And this is so this becomes a problem of finite, just a network problem. Okay, it's a network problem. So let me show you in two cases in two networks, right? So let's say is we use this this is a positive bomb, and this is a negative bomb. So the first network is a symmetrical network. Right? You take a polygon of size, some size, and you put all the plus, okay, bumps, and then on the edge you take plus minus plus minus plus minus plus minus. And you can show this is a balanced network, and it is closable and is also flexible. So, and for this kind of network, and you can build up the sign changing solutions. You build up sign changing solution, but this network is still still has some symmetry, right? Right? And we want a solution that has no symmetry. So so this is how you choose the L in terms of the numbers, right? You can choose the L in terms of numbers. So I will not, and it's a dedicated balance between the L and the numbers, okay? You have to compute. And you can, there's also, take a non-symmetrical network. So this is a non-symmetrical network. So this network has no symmetry, And then you can place positive, negative, and on this network. And then this you can show that this network is flexible, is closable, flexible, and balanced. So for this one, you can build up a solution with no symmetry. Right? With build up a solution with no symmetry. So this is the first application. For the Klein-Gordon, we artificially make up a parameter, which is the number of bumps, and we use this parameter number of bumps to build our solution. This is the first application. So any questions? Any remarks? All right, so let me go to the second application. Which is very recent. It's optimal quantitative estimate for Stewart decomposition. So we have the standard solving of inequality. We take the solving of inequality, and we know that the Euler-Lagrange equation for the solving inequality is this is the Yamabe type equation, right? And all positive for solutions for the Yamabe problem are so-called Tonality bubbles. So Bianchi and Angelo in 1993, they obtained the first quantitative estimate of the solving of inequality near the minimizer. So you can find what is the remainder of the solving of inequality, and they found they have this type of remainder estimate. Okay, this is so solving inequality measures how close the remainder is, how close to the Tonality bubble. Okay, close to the Tonality bubble. So a more natural and more challenging question is whether a function which almost solves the Euler-Lagrange equation must be quantitatively close to Tonality bubble. And should we exactly prove the following result? We call the Stewart decomposition, 1984. And what he proved is, if you know the energy is between has mu level of energy, okay? If you have some sequence of functions which is D12, and if you already know this is the Lagrange multiplier, the Euler-Lagrange multiplier is certified almost in the weak sense. So it's h-1 goes to 0. Okay, then Stewart said you can decompose your problem into the Tonality bubbles, and then then the distance between you and the Tonality, the core piece of Tonality bubble is small. Okay, so this is called a Stewart decomposition. So this is quantitative, but not quantitative. So Figani and Gallardo in 2020, and they prove a quantitative version of Stewart decomposition, and which is a linear relation. So if your Euler-Lagrange equation goes to 0 weakly, then your distance between you and the core piece of the Tonality bubble, you can control linearly by this Euler-Lagrange equation. Right? And for dimension n greater than 6, and they conject that for n equals 6, this relation is no longer linear. You should have a log. And for n greater than 7, and this relation should be some alpha, for some alpha less than 1, strictly less than 1. And they have counterexample shows that if alpha equal 1, this is no longer true. So, okay, so, but the precise value of alpha is not known in the conjecture because it's quite complicated to compute these two quantities. And so in a very recent work, and just last week, so we use this reduction method, right? Finite dimension reduction method, and we solve the problem completely. So for dimension 6, and we show that the right power, the right quantity is gamma times log square root of gamma, square root of log. And in dimension n greater than 7, what the alpha, the number alpha is n plus 2 over 2 times n minus 2. And we show that this inequality is optimal. So this is the optimal quantitative estimate. Okay? Optimal quantitative estimate. Okay, so how do we prove this? We prove this by reduction method. So you take the distance between you and the Tananti bubble. So of course it will be a 10 because we know that this is close to the Tananti bubble. It will attended by some Tananti bubbles. And so we take the difference between you and the Tananti bubble. And so the difference will satisfy an equation, a nonlinear equation, right? And the f, this is the Lagrange, this is the error, okay? This is the error. And the f is also orthogonal, right, to the Tananti bubbles. So the question is, how do we estimate the alpha norm of gradient rule in terms of the right-hand side? That's if we can have a quantitative estimate of gradient rule in terms of the h-1 norm of f, then we're done. And this is exactly what we prove. So how do we estimate this in terms of this? Okay, and the right-hand side is only in the h-1 norm. Okay, so what the key idea is to obtain the precise behavior of the first approximation for the by standard finite dimension reduction. So you just take your Tananti bubble, you do a finite dimension reduction, and so this is a classical finite dimension reduction I introduced last week. But now the only problem is the critical power, right? So we need to compute this finite dimension, compute the next order of this rule set. And so we need the asymptotic behavior of the rule, okay? Now the problem is you have a bubble tower, bubble cluster, and even bubble tower and the bubble cluster, they are interrelated. You have many situations. So let me just show you the bubble cluster case. So the one bubble case, in the one bubble case, we can do finite dimension reduction, and we just use the weighted solvent norm, and we get the reduction, okay, in the one bubble case. Now in the two bubble case, and if we have a bubble cluster, which is two bubbles that are far away, and we can use this type of norm and to compute the inner estimate. We use this type of norm to compute the outer estimate. And then with this inner and the outer estimate, you can compute the outer norm precisely. So this is the second application, the Stewart decomposition. Now I will quickly discuss the third application, which is I found is also quite interesting because this is another situation in which you don't have a small parameter. Okay, so I'm going to discuss the so-called isolated synchronicity for the fractional Yamabe problem. So if you look at the fractional Yamabe problem, with one synchronality, you can classify. You have the Caffarelli, Jin, and Sarah and Shum. They classify the synchronality and you have reduced symmetric solutions, right? For these singular solutions. So the question is, can we group the isolated singularities by finite dimensional reduction method? Right? Now, the isolated singularities are completely different from the bubbles. Okay, right? From the Tonanti bubbles. These are isolated singularities. How to group the isolated singularities? And yeah, and the answer is yes. We can, given any arbitrary points, we can group this finite number of isolated point, singularity point. Now, when gamma equal 1, and this is proved by Mazur and Paca in 1999, but using not using the finite dimension reduction, but using some linearized estimate. So let me show you how we can reduce this problem to finite dimensional reduction method. Okay, I think this is quite a okay. So the regionally symmetrical solution, the isolated singularity, we call the Danelli solution. Now, the Danelli solution, we think that the Danelli solution is an infinite sum of bubble taus. So think about the Danelli solution as infinite many bubble taus. They are at the same place. Okay, and now if you have a two isolated singularity, so you have two infinite many bubble taus, and what you need to do is to perturb each of the bubble, okay, in the scaling parameter and in the translation parameter. So you have to perturb all these bubbles. Okay, so what you need to do is to do a sort of reduction method, but with infinite many bubbles. Right? So you see that you have infinite many bubbles. So you have infinite many Lagrange multipliers, and you do a reduction method with infinite many bubbles, but infinite bubbles at the same place. Okay, and this you can do. You can use the inner and the outer aspect and all this. You can do this infinite many. You get infinite many Lagrange multipliers. Now to solve the infinite many Lagrange multiplier, and you're going to get some infinite dimensional total system, total matrix. And it turns out that we can solve this the inverse of this total matrix explicitly, because this is nothing but discretization of the Laplace operator in 1D. And this is exactly what we use. We can solve the inverse of this matrix explicitly by viewing this as the discretization of U double prime, okay, the Laplacian. And then the only thing left is to adjust the first bubble, which you perturb the location and perturb the first bubble by the Danelli parameters. So what I want to just mention that this third application is, even though the finite dimension reduction, you can, if you have infinite many bubbles, you can still use this finite dimension reduction and to construct solutions. The way is you have to view this as infinite bubbles. Okay, so this is some 3 applications of finite dimensional reduction method. And so are there any questions, any remarks, any questions? Okay, if I don't see any question, I will go to the second lecture, and I will discuss the infinite dimensional reduction method, I will discuss what is so-called inner and outer green scheme. Okay, so in the first lecture, we did the problem of construction solution with finite many or infinite many bumps, but all this configuration space are points. Okay, you may have infinite many points or infinite many, okay, but these are the bumps, okay. So in the second lecture, we'll generalize this idea to the problem of construction solutions concentrating on high dimensional cells, such as curves, surfaces, or minimum surface of core dimension, right? Or core dimension 1 or core dimension 2. Now, as in the finite dimensional case, and we proceed in 2 steps. In the first step, we solve the problem along the tangent space. Okay, and this amounts to imposing infinite many orthogonal conditions. And in the second step, and we move this curves or surface and in the normal direction and to find a true solution, right? Okay, so the model problem I'm going to take today is the Clang equation, and which is a standard model for many problems, right? Clang equation. So you have a -1 and a +1, right? U minus U cubed. And the one-dimensional solution you can write down explicitly, and this is the building block I'm going to use today, right? For the high dimensional solution. So we take the one-dimensional solution, and let me call this W, which is nothing but the tangent hyperbolic x over square root 2, right? So you connect -1 to +1, and this is the one-dimensional profile, the one-dimensional solution. So, so this is a typical equation. This is called a double wall potential, right? And so you have a double wall, 2 minimum and a -1 and a +1, and the 2 minimum have the same depth. Okay, so this is called a double wall potential, and this -1 and +1 are 2 phases. So you have like 2 different phases. So this is an important model for phase transition, superconductivity, mathematical biology, and the image process, and the big data, and the many applications. And this is a basic model in many physical problems. And there's a deep connection with the minimum surface. So let me just explain to you why this problem is related to minimum surface. So to discuss the relation between this problem and the minimum surface, let's put a small parameter in front of Laplace and put a large parameter in front of the potential. So, and this is the so-called bounded, the Epsilon version of Clang. And so in a bounded region, and this is the energy function, right? Now, so if you want to minimize this energy function, then U must be close to -1 or +1. So what you get is inside the domain, most part will be +1, and the most part is -1. And in between, you have some interface. Okay, and this is the interface we want to discuss. Now, formally, if we compute the energy functional, okay, and then formally, you will be just like the parameter of this interface, right? Formally, it will be this J, this energy function in bounded domain. If you have this kind of behavior, the solution is like the parameter. Okay, the energy function is like a parameter. So the critical points of J epsilon omega will be like a critical points of the parameter. And we know the critical points of parameter are mean curvature, a zero mean curvature, which is a minimum surface. So formally, And you see that the ordinary Lagrange equation, the Untitled equation, should correspond to the minimum surface, right? This is a formal level, right? This is a formal level. And about this, you can make this rigorous energy level if you have local minimizer, and then you can show that the interface, the nodal set will approach the minimum surface, so which is the mean capture equals 0. So this is by Modifier and Motola and the gamma convergence and the Quang Steinberg by gamma convergence. And if I have a local minimizer, and then you can prove a C1 alpha estimate for the interface. And you can also have the quantization if a bounded energy by Hutchison and Tanegara. And for stable solution, you can also prove C1 alpha estimate, Tanegara and Wikara Masakura. And from C1 alpha estimate to C2 alpha estimate, this is what I did with the KD1. And if I have time, I will talk about how we use the reduction method, how we use the infinite dimensional reverse GUI method and to prove the C2 alpha estimate, okay, if I have time. And recently there's large literature on the relation between Annenkang, the minimax theory of Annenkang, and the corresponding theory in minimum surface like Gasper, Garacco, and the Childish Mantonitis, and Fernandez and the Neves, and so on. Okay, so in this talk and in this lecture, I will describe a precise correspondence between three-dimensional Annenkang equation and minimum surface in R3. Okay, I will give you a precise correspondence between these two problems. Right? So, and I will show the proof. I want to use this as a model problem to show the inner and the outer GUI. So what we're going to show that there is a precise correspondence between entire solutions of Annenkang and the minimum surface embedded minimum surface theory in R3. So now let me start with some preparations. Let me try to some notations, okay, some definitions. Are there any questions? Any remarks?
Just make sure there's a, with the left hand side, you have a dimension n.
Yeah, you should be 3. Yeah, this should be
3. Okay.
Yeah,
Just make sure. Yeah. Okay.
Yeah. Okay. Yeah. Thank you.
Mm-hmm.
This is my typo. Yeah. Okay. So let me now first discuss the minimum surface. Suppose I have a complete embedded minimum surface in R3 with a finite total curvature. So finite total curvature means that the second fundamental form is L1. Right? So this means a finite total curvature. And for minimum surface, we introduce so-called Jacobi operator, which is the perturbation of the minimum surface in the normal direction, right? So this is the Jacobi, which is the Laplace Bernoulli operator in M, okay, and plus the second fundamental form. Now, since this is a minimum surface embedding R3. Now, if a minimum surface not embedding R3, if the ambient space is other Riemannian manifold, you're going to see the rich curvature here. But okay, but since our case is the Euclidean space, so you only see this type of Jacobi operator. Okay. Now, so a smooth function we call the Jacobi field is if this equals 0. Okay. So the kernel of the Jacobi operator is called a Jacobi field. Now, in for minimum surface in R3, your automatically here have 4 Jacobi fields, and you have translations because you translate the minimum surface, it does not change, right? and you rotate the minimum surface, it does not change. So automatically you have 4 Jacobi field, which is translation. This corresponds to translation, and this corresponds to rotation in 1. And the others can be a combination of these 4 Jacobi field. Right? So I call the mu of y is the normal direction. So now we assume that M is non-degenerate if these are the only Jacobi field. Okay, and this is what we need. We need this this assumption. So these are the only Jacobi field for this Jacobi for the kernel. Right? So only rigid motion. Right? And the 2 important properties we're going to use later, because first is M contains only finite many ends, and each end is catenoid, and this is or logarithm. Okay, this is Aussermann's result in 85. And the M is orientable. So for minimum surface, inverted minimum surface, if you look at R3 minus M, and you consider precisely 2 copies. Okay, and this is important because later we're going to assign 2 values. On 1 copy, we assign -1, another copy assign +1. So we need this orientable. Okay, need this to be orientable. So an example of non-degenerate minimum surface is the standard catenoid. This is a catenoid, and we have 2 ends. This catenoid has 2 ends. And another example is a Costa surface, Costa-Hoffmann mixed surface. And in this case, you have 3 ends, and then you have some holes inside the. So this is a minimum surface. Right? This is a minimum surface. Okay. So the result I'm going to prove, I want to use the as a model problem. I want to prove is this this theorem that I proved with the Pino, Krasik, and in 2013 in the JDG, and so the full version is on my website. Is much longer, but the printed version is only half of the pages. You can download the full version from my website. So let's take a dimension 3. Let M be a minimum surface embedded, complete with a finite total curvature and non-degenerate. Then we can find a family of a bounded solution to the Allen-Cahn. Okay, so let me stress: there's a family of a solution, not just one solution we found. We found a family of solutions which depends upon some small parameter alpha. And this solution concentrate the nodal set is the nodal set of U is M over alpha. So you take the minimum surface, but you scale the minimum surface by a small parameter. So your minimum surface become large, enlarge your minimum surface. So this is the solution. Right? And we have a solution. The nodal set is almost like M over alpha. Right? And furthermore, U is non-degenerate. Okay, so like a minimum surface, the only kernel, bounded kernel, consists of rigid motions, so translations and rotations. Right? And even more, we can say that the index of the minimum surface, you can define index of the minimum surface, precisely equals the most index of U. So you have all the information of the minimum surface can be transmitted to the solution, to the Allen-Cahn. Everything, right? So the non-degeneracy, the most index, and the nodal set. Right? So this is a one-to-one correspondence between minimum surface and the Allen-Cahn equation, solution to the Allen-Cahn equation. And so in my lectures, I'm going to prove this one, prove this theorem. So any questions?
I have a question because you for the Allen car earlier, you introduced the small parameter epsilon.
Yeah,
What
yeah,
do we-
it's a in front of yeah, exactly in front of
the alpha. How?
Yeah.
What
I
is
call the
alpha? That alpha related to epsilon some way?
Yeah, alpha equals epsilon. I should write that. You should,
Oh, alpha
the
equals
small-
epsilon.
Yeah. Okay.
Okay,
It's,
good.
Yeah. Okay. So and okay. So let me explain why we have this alpha. You know, what is the alpha? Right? What is the alpha? Because in the problem before, we don't have alpha, just plus u minus u cube, right? This problem has no small parameter. So what should be the alpha? Okay. So what is, and this is very important. We need this small parameter. So we have the simple observation is the minimum surface is a scaling invariant, right? You take a minimum surface, suppose M is a minimum surface, you rescale, right? You rescale, okay? And the surface is still a minimum surface. So if you consider a single perturbed Allen Clang as before, you know, like a bounded domain, okay, you can put an alpha square in front of Laplace because this is in the whole space. You can put a small parameter anywhere, right? You can put a small parameter in front of Laplace. Then this will correspond to the original minimum surface, right? Now, for the problem without the small parameter, this will correspond to enlarged minimum surface, M over alpha. So you think about, we're now building a solution to Allen Clang for a rescaled minimum surface. This is actually what we're doing. Okay? That's the small parameter. The small parameter is this one, is this alpha here, is from the minimum surface. Okay. So this proof theorem will be proved by infinite dimensional reduction, right? So
by the way,
yeah,
you also have a W there. So can you have W? So when you consider
W is the 1D solution, the one-dimensional solution.
Okay, I see. Okay.
Is a tangent hyperbolic.
Oh, I see. Okay, thank you.
Yeah. So I will prove this by infinite dimensional reduction. So let me just use the code f of u is u minus u cube. I don't want to write this all the way on the lecture. So how do we use the infinite dimensional reduction? What are difficulties? First, the kernel corresponding to 1D solution has infinite many kernels, right? Infinite many. And the geometric coordinate near the minimum surface is only defined locally. So you take a minimum surface and you can define so-called Fermi coordinate, but this Fermi coordinate is only defined locally. So how do we go from this local coordinate to a global coordinate? And so this is the so-called inner outer growing scheme, which I'm going to introduce. And the reduced problem is highly non-local. And so we need a good Jacobi operator theory. Now, okay, so so this is an outline of my the proof. So first, I will give a property of the building block. Okay, and then I will discuss the so-called Fermi coordinate. After the Fermi coordinate, and I will introduce the first approximation and the first improvement, and then the inner outer growing. So how we go from the inner, how we go from the local coordinate to a global coordinate, and we can reduce epsilon to a global solution. Okay, and finally to a global equation. For the global equation, we use the infinite dimensional reduction. Okay, for the global for the inner problem, and then with the two steps, and for second step, we use the Jacobi operator. We need some theory of the Jacobi operator, and finally we can prove the theorem. Okay, so this is the outline of my the proof, and what I want to emphasize is this inner outer green, and this is this is a way to reduce your problem to the whole space, okay? And this is what I'm going to also use for the heat equation and for the Fujita equation. So I will explain this quite well just for this problem, because the how we do the inner outer green, and how we do and then use the Jacobi operator. Yeah. So okay, so do we still have 10 minutes, right?
Yeah, we can go maybe 7. Yeah, I think.
Okay, yeah, okay. So let me start with the 1D problem, right? Building block. So let me just explain the building block. Even though it's 1D, it's very simple. Okay, you should know everything about this. Okay, so the 1D problem is exponentially close to 1 on one side, and it's close to -1 on the other side, right? And also it's a monotone, right? This is a monotone. So from the monotonicity, and you can say that the eigenvalues for the linear operator in 1D is very simple. The first eigenvalue is 0, which is corresponding to W prime. And the second eigenvalue, okay, is positive, right? And from this, you get some spectrum gap. And this is easy to see. So if your solution is orthogonal to W prime, then you have some spectrum gap. Okay, this is very easy to 1D problem, very easy to do. Okay? But what's non-trivial is the same thing holds in higher dimension. So, and we're going to prove that what we're going to need later is that this solution, which is a 1D solution, and this solution is also non-degenerate in higher dimension. So you just simply extend this solution in all other dimensions, okay? And let's look at the linear operator. And so you just simply add 2 more directions, okay? This is a Laplace operator. And what we want to prove is for this new linear operator, you have more Laplace here. For this new linear operator, the same thing holds. The only kernel is W prime. It's constant times W prime. Okay, this is the only solution, bounded solution. Right? So, and this is what we're going to prove. And then after this, I will stop here today. So how to prove this? Okay. And so first, so you take this solution, we just know the solution is bounded, right? And first we want to show the solution is exponential decay, okay? Uniform in Y. Okay, and this is important because later I'm going to do integration. So you just know phi is only bounded, but now you can show that in one direction phi has exponential decay. Why? You just use a barrier function. So this is a barrier. You take an exponential decay in one direction, but in other direction you take exponential growing functions. Okay, to take an exponential growing functions. So this will control the other directions. And then you can check that these are solutions, okay? This is a barrier. And so since your solution is bounded, and so you can use this to control at infinity. And so you get, by maximum principle, you get this. And then you can just simply let this epsilon go to 0, and you get exponential decay in one direction. In T, right? And this is important because, and similarly, you can get the dy is also exponential decay. So with this, now it makes sense. I can just integrate one direction, right? dt. This makes sense because my solution exponential decay in T. So this makes sense, okay? This integral makes sense, okay? So now we just project the solution, your fixed Y, you project your solution in W prime. Okay, and then you can check that the new solution, the projection also is a solution to the linearized operator. And now the solution is orthogonal for all y. Okay, orthogonal in double prime. Fix each y is orthogonal. So now let's compute this, the L2 norm. Okay, L2 norm in dt. And you compute the Laplace of this L2 norm. And you just do some simple computation. And you found that the Laplace of the L2 norm has a sign, it's non-negative. And the reason is that this part is non-negative, okay? Because we also have the orthogonal condition, okay? So this part is non-negative. And so hence, and this is bounded, and you have a subharmonic function. So you have, by maximum principle, so phi must be 0. And this shows that this must be 0. So you get this function, right? And this function is just a harmonic function, and so it must be constant. And so you prove that the kernel must be just C double prime. So what I have done today is to study the non-degeneracy of the building block in high dimension. Right? And we know the non-degeneracy of the building block in 1D. This is very easy to see. But now we show that the W is also non-degenerate in high dimension. Okay, non-degenerate in high dimension. So next week, so I'm going to introduce what is Fermi coordinate, and then we're going to do some computation on Fermi coordinate. Okay, first approximation, first improvement. Then I will introduce the inner-outer green scheme and the infinite dimension reduction and the theory of Jacobi vector and prove the main theorem. Okay, and which is this one. This is the main theorem we're going to prove next time. Yeah. So maybe I stop here today. And are there any questions?
All right. Thank you, Juncheng, a lot for a very nice, very detailed talk. And it's now open if you have any questions.